Hello, my name is Marco Riani.
And my name is a.c.atkinson. Today we are going to talk about Chapter 9, which is concerned with the important point of model selection. We have a regression model that we want to fit to the data, and we have p terms in the model. So there are p-1 possible t-tests that we can do for the variables. If we find a variable that is non-significant and remove it, then particularly if the explanatory variables are highly correlated, the values of the other t-statistics will change. So this is very confusing, and we need to find some better way of choosing the subset of significant or explanatory variables that give a good description of the data. There are many numerical methods, arbitrary numerical methods, one could describe them as, which consider ways of adding or subtracting terms from the model. You can start from all the terms and subtract. You can start from none and add one at a time. And then you can find the model that gives you the minimum residual sum of squares. However, these are purely arbitrary and do not have any statistical underpinning. Methods for model selection that do have a statistical theory underpinning them are typically information criteria, where you maximize the log likelihood of the observations and then penalize them by some function of the number of parameters in the model. Two of these that we should not be discussing here, but are described in the book, are a.c.atkinson's information criterion, AIC, and the Bayesian information criterion, BIC. These are general criteria for choosing models. They are not particularly tuned to the regression problem. The thing about the regression problem, compared with many other statistical problems, is that we require an estimate of sigma squared, which is a rather different parameter from the rest of the parameters. Mallow, in 1973, introduced the CP statistic for the selection of a regression model. It's a special case of a.c.atkinson's information criterion, provided you make particular assumptions about the estimation of error variance. The application of AIC to the selection of regression variables requires an estimate of sigma squared. On the assumption of the absence of outliers and a correct model, the unbiased estimate of sigma squared comes from a large regression model with an n by p plus matrix x plus. P plus is greater than the number of parameters that we expect to find in our final model. X is a submatrix then of x plus. The unbiased estimator of sigma squared from regression on all p plus columns of x plus is s squared, that is the residual sum of squares for p plus parameters divided by n minus p plus. The idea of Mallow's CP is to penalize the residual sum of squares of the particular model that we're interested with p parameters by a function of the number of parameters in that model. As the number of parameters in the model increases, the residual sum of squares decreases. But this can lead to overfitting, in which the predictions from the fitted model are highly influenced by unimportant random fluctuations in the data. Mallows therefore suggested penalizing the decreasing residual sum of squares with p by a penalty function increasing with p of the form plus 2p. If we then estimate sigma squared by the residual sum of squares from the large model, we get the form on the right-hand side. So it involves two residual sums of squares, that for the model that we're interested in, and that provides, after scaling, the estimate of sigma squared. Mallow's CP is highly related to a.c.atkinson's AIC, but derivation of it in the regression context is that it provides an estimate of the mean squared error of prediction at the n observational points from the model with p parameters, always provided, of course, that the full model with p plus parameters yields an unbiased estimate of sigma squared. We're going to use CP in plots and we need to have some idea of its distribution. Mallows and Gilmore have both showed that CP for all n observations is distributed in this form here, where the statistic calculated f has an f distribution on p plus minus p and n minus p plus degrees of freedom, so that we can get bounds on the value of CPN. This is the statistic for all observations. We're going to use the forward search, and we will be estimating for using subsets of size m. We obtain the values of the CP statistic in the forward search by replacing n in 9.7 by m, and we are estimating both sums of squares of interest from the subsets that we have. That is the one for p parameters and the one for p plus parameters that provides the estimate of sigma squared.
We have a forward search for each model combination. In order to summarize all these forward searches into a single graphical tool, we have introduced what is called the generalized candlestick plot. The name candlestick plot comes from the fact that it is very close to the financial plots with candles.
If we include a constant in all the models that we are considering, there will be 2 to the p plus possible models to be considered. Often we won't consider models in which there is no constant, but even so, the large number is, if there are 10 explanatory variables, we will have to look and try to condense and understand roughly 1,000 forward searches.
In order to illustrate how the candlestick plot works, we recall the ozone data.
As a comparatively small example, with sufficiently many potential explanatory variables to be interesting, we look part of the data on ozone concentration, which was used in the paper on JASA to introduce the statistical procedure ACE, which we have described elsewhere in this book. In the full data, there are a series of 330 daily measurements. We first analyzed the first 80 observations, which start in January, and one of the variables that is of interest is ambient temperature. In the part of California in which these observations were taken, ambient temperature can be taken to be increasing approximately linearly. So we use a linear trend for temperature,
and we add it to our X matrix, so that as explanatory variables we have time plus 8 explanatory variables. In total we have 10 variables including the constant. We do a forward search for each possible model in the interval 5-9, so the minimum number of variables considered is 5 and the maximum number of variables which is considered is 9. Then we show a summary of all these forward searches through a plot which we called candlestick plot.
Well, it is not actually true that we show a summary of all of them, because of those which are clearly very poor, we do not bother to include in the plot. So here we have the number of variables in the model running along the bottom from 5 to 9. We have horizontal lines in each plot which give us the quantiles of the distribution of the CPM, and then we have a vertical line for each model that we think might be of interest. We have to be careful that our understanding of the value of CP for each of these models is not badly affected by outliers. We take a range from 0.8 of the number of observations in the sample to 0.95 to represent a central part that we consider gives us a reasonable estimate of CP. This central part is shown by the vertical lines in the plot.
The minimum value of the vertical line is the minimum in the central part of the search. The maximum value is the maximum value of the CP for that particular model in the central part of the search.
Within these lines, you will see that there is a box, and it gives the mean and median of the values in the central part of the search. It's filled in, this blue color, if the mean is less than the median.
And vice versa, it's not filled if the mean is greater than the median.
The red stars, which you can see sometimes above and below the line, are the values in the final part of the search, if these lie outside the range of the CP values in the central part of the search. So this is an indication that some of the last observations to enter, which may very well be outliers, are appreciably changing the value of CP. The other thing in the plot is the unfilled blue circle, which is the final value.
For example, let us look at a particular combination. This suggests that the values of CP are always inside the bands, that the final value is the largest value, and then we have a value here shown with the star that belongs to the final part of the search and is smaller than the minimum in the central part of the search. For example, let us concentrate on the model time and variables 4, 5, 6. This model contains 5 variables because there is the constant. You can see that this model in the central part of the search is always inside the bands, and the minimum and maximum in the central part of the search is well inside the bands. Then the mean and the median in the central part of the search are very close to each other. However, there is a value which still is inside that belongs to the final part of the search, and then the last unit to enter the search causes the trajectory to go out of the 97.5% upper threshold. It is enough that we click on this candle in order to see the details of this forward search. And you can see that indeed the final value causes rejection of the suitability of this model.
Of course, this use of CP is just the first start in model building. It indicates to us a few linear models which it's worth learning more about. In this case, we checked the model using Ravers, starting from the log transformation of the response and a linear time trend. There was no indication of further transformation of these two variables. 3 outliers were identified, and the least significant variable had a t-value of 4.8. In practice, we will probably be happy to use this simple model. The other panels show models that have extra variables. We notice that many of them, in fact, fit very nicely within these final bounds, with just occasionally the last observation lying outside. This is very clearly showing us that in this particular set of data, we do not need to include anything like all the explanatory variables, that 5 are enough, and little more is probably gained by going to 6 or 7. If we do go to p is equal to 6, we see that there are 2 models there, time 4, 5, 6, and either 7 or 8, both of which are fitting nicely inside the interval, and that the box has now become much narrower, indicating much less variability in the values of the CP statistic towards the end of the search.
For example, let us see the forward search for this model time 4, 5, 6, 7. All values inside the search are inside the bands. You see that the final one is inside the bands. It is close to the sort of 80 or 90% quantile of the F distribution.
These 2 panels of CPM that we have shown you show how very jagged the values of CPM are during the search. It jumps up and down. In some of our earlier work, we tried plotting the values of CPM, and they are so variable as to be highly non-informative. The candlestick plot provides a very cogent way of ordering this mass of data in order to extract the information from it.
Finally, notice that it is also possible to select a series of models, more than one, and to see the corresponding trajectories. So that this is really an interactive way where you can interact and selecting a set of models and see the corresponding trajectory. And this is the thing that you were mentioning before, that the trajectory during the search can be wild. Now look at these models. There are observations that when they enter the search, these models respond in a similar way. This is the great information that we have by monitoring. Every time that we see this information, we ourselves are surprised by the amount of information that we have during the monitoring. On top, here you have the number of selected searches and the values of small p that have been considered. Okay, now we move to the analysis of the full data set.
So there are 330 observations. In the reduced ozone data, starting from the beginning of the year, it was possible to explain the effect of time by a linear trend as the weather warmed towards summer. For 330 days, we take a symmetrical time trend, increasingly linearly to n over 2 and then decreasing. Figure 9.2 shows the resulting candlestick plot. In general, this is very different for the reduced ozone data. For the reduced ozone data, we found a satisfactory model for 5 and certainly satisfactory models for p is equal to 6. Here, we need many more explanatory variables to get a fully satisfactory model. So here, we find good models for p is equal to 8 and 9. However, we find very few models that are satisfactory for p is equal to 7. But we do, however, find one really seemingly very good model. This is one with time and variables 1, 2, 3, 4 and 6.
In order to have greater information about the trajectory of this model, put option CP brush, and then we reshow this model, and then when we select it, we can see that in the central part of the search the trajectory stays inside, also the final value is inside, is not the most remote one. Now let us see in more detail this trajectory, and here it is. As anticipated by this candle, this trajectory is always inside the search, and the final observations do not seem to appreciably change the value of the trajectory of CP.
Note that for this example, we have taken the so-called central part of the search to be from observations 264 to being 313 observations.
So the central part of the search is defined as m going from 0.8 multiplied by n up to 0.95 multiplied by n. Finally, note that when we select the particular trajectory, in the plot which comes out, we have the quantiles, the lines associated with the quantiles of the F distribution 0.025, 0.975, and also the line associated with the median. On the other end, here we don't have the line associated with the median. We have used this plot throughout the book, also in chapter 10, for a confirmatory analysis. That is, for example, when the number of variables is much greater, then we use the lasso and or other techniques for finding a reduced subset of variables, and then once that maybe the data have been transformed parametrically and or non-parametrically in the transformed space, we give the candlestick plot in order to understand the stability of the different models and in order to have additional information about the variables that are most present inside the best models.
In the rest of Chapter 9, we consider these regularization methods that we've just been discussing, like the lasso and sparse LTS. But our focus in this video has been on the use of the candlestick plot for reducing the large amount 2 to the p plus possible models and finding which variables are required by good models. It has been interesting to see that in our initial small example, relatively few variables were required, whereas when we expanded the data to 330 observations, a more general model was necessary.
Thank you for watching and see you to the next video.
Arrivederci.